Recording is rolling. It is Thursday, August 28th. So, a while back, I gave you guys these linear motion puzzles. We're going to look at some of these today. Now, on the backside, there are a bunch of spaces for graphs. Look at this: X versus T, V versus T, A versus T. They should look familiar from yesterday. So, these are due on Tuesday. Again, we'll do some of these today we'll be looking at. And then, you guys know there's a quiz tomorrow. So if you have spare time after the quiz tomorrow, which I think most of you guys probably will, but I'll see. We'll find out tomorrow. Then, of course, you can work on your linear motion puzzles then. And we have Labor Day weekend coming up. So, yeah. Then Tuesday, I'll pick this page up for you guys. Okay. So let's do a quick quiz review here. We'll do a quiz review, and then we'll solve some linear motion puzzles, and then let's do the end of class stuff. Okay. So, I want you guys to know these things. Here, let's go at this list. Vectors and vector components, some trigonometry, scaling, graphical relationships. Can you solve some basic algebra equations? I have a few questions that might be related to that carbon incline lab because we did spend a few days going over that. So, what are certain graphical relationships? How far does the car go as a function of time? How fast is a function of time? Those kind of questions. Okay. So, I got some guided posters. Do you guys know Pythagorean theorem for a right triangle? You guys do that? You guys can navigate that? What about the area of a triangle? Can you guys find the area of a triangle? Okay. Which, by the way, that turned out to be helpful recently. We were trying to derive how far something moved as a function of time in an accelerating environment. Turns out to be the area under this d versus t curve, which might look triangular, or part of it might look triangular. Right? So that was helpful recently for that. Showed up surprising place. Right? Vector components. If I give you a right triangle and the hypotenuse in one of these reference angles, acute angles as a reference angle, can you find the two legs? And the physics application is normally there's some kind of vector. Like I might have a force vector, a displacement vector, a velocity vector. Maybe I'm pushing with some force, like up and to the right. I want to quantify like how much up and how much to the right. Well, if I give you this angle, then you can determine that. So this side B is C sine theta. This side A, which is adjacent to the reference angle, would be C cosine theta. Okay. Can you guys extract this angle from knowing information about the sides? Can you guys do that? Okay. If it's the two legs, I could do an inverse tan. If it's guys, what if it was side B and side C? That would be an inverse what? Yeah, inverse sine, okay. Which you may have done to calculate the angle on your incline for the carbon incline lab, right? Okay. And then okay. So you need some kind of inverse trig function to extract an angle, and that's what this one says down here. Okay, you guys see that? Right. Scale. No, I did have a scaling question. After I printed all the quizzes, I realized somehow I misprinted it on the quiz. So, oops, you guys won't actually get the scaling question, but I'll ask it now. I did have a question ready to go about. There was Sheldon the short elephant and Timmy the tall elephant, and if you had suppose the ratio of their heights was like 3-1, which matches this poster, right? So Timmy the tall is 3 times Sheldon the short. Okay? What if they're both casting shadows? What are the relative sizes of the areas of their shadows? Wait. Yeah, it's a square relationship. So if Timmy the tall is 3 times as tall, then his shadow is how many times as big? 9 times, right? What if you weighed those two elephants? How much does Timmy the tall weigh compared to Sheldon the short? 27 times. Yeah, 27 times, as long as they're proportionally the same. Okay. Yeah. What if their heights were a ratio of 2-1, which doesn't look exactly like my picture, but it's the same principles that apply. Okay. What if Timmy the tall is only twice as tall as Sheldon the short? What would his shadow be? How many times bigger? 1, 4. Be 4. 4. This would be a factor of 2 squared. 2 squared would be 4. Okay. And if you put them both on scales, how much does Timmy weigh compared to Sheldon? 8. 8. Yeah. Because he's twice as tall and weight. Okay, that occupies volume. It's like a 3-dimensional concept, right? Or mass occupied volume. So 2 to the power of 3. Yeah, that would be 8. Okay. All right. So I do want you guys to know that because the scaling property is going to show up later in the class, if not tomorrow. Okay. All right. Algebra. Can you guys solve some basic algebra equations? Like if I give that to you guys, can you guys solve for x? You see that? I got a couple of these, so if you downloaded that book, you got a couple of examples there. Okay. Let's do algebra shuffling, which is really similar concept. Okay. So could you guys say 3 times 8, is that equal to 4 times 6? Is that the same thing? Okay. Now, if you start with that, see, what could I do? Could I, let's say, take this 3 and divide it down to the opposite side? Could I do that? The 8 equals 4 times 6 over 3, like this right here. Right. Or what if I do this? What if I well, okay, yeah, okay. You guys see every single one of these gold boxes says exactly the same information. It's just free range somehow. Okay. Can you guys do that with letters? Ooh, it's letter time. So if I replace the numbers with letters, same principles apply. So you guys can cross divide and cross multiply and put fractions and fractions. Right, you guys can do all that. Okay. All right. If I ever spit out the phrase y equals mx plus b, I'm referring to some linear relationship where the plus b is the y-intercept, right? And the m would refer to the slope in this context, something like that, like rise over run slope. Okay. Now, oftentimes in this class, this intercept, like back when you're doing labs, this intercept ends up being 0. So it goes through the origin, and I would just call that a direct relationship. Because if you have a direct relationship, if you triple x, does y also triple? Yeah, sure does. Right? Because what if it's a really shallow slope? What if it's like down here? Here, if I triple x, does y still triple? Yes, it does. Right? What if I have a really steep slope like this? I triple x from like 1 to 3 is like from here to here. Would the y value go from like 10 to 30? Would that also triple? Yeah. Okay. So it doesn't actually matter what the slope is, right? If one triples, the other triples, as long as it's a direct relationship. Okay. Now, what graphs do you see in this class? This is a pretty comprehensive list from any lab that you do in this class. Any graph that I could ask you to ever draw, right, all the way through May, is probably covered by this page right here. Okay. Now, the only one we haven't come across yet is sinusoidal, so I think that'll show up probably in about January or so. But all these other ones, actually, I got them within reach right here. Let's go through some. So, you guys remember the car down the incline? Let the car go. Zoom, zips down. Zoom, right there. How far is the function of time? That's a what shape? Parabola. Okay. Now, anything that's ever a parabola is if you let it roll for, let's say, double the time. Guys, double the time corresponds to how many times the distance? 4 times. Aha, because the factor of 2 squared. That's what a parabola is, right? What if you let the car roll for 3 times the amount of time? How many times the distance is that? 9, because 3 squared. Actually, let's see if that's true. Because it looks like maybe the point 125 is pretty close. You guys see after 1 second, maybe 0.25 centimeters. So let's say 3 times the time. Guys, what's 9 times 25? If you have 9 quarters, how much money do you have? Is that, yeah. 9 times 25, that's what, 225? 225 about? Okay. So, shit, in 3 seconds, it's about 225. Oh, yeah, actually it is. All right, you guys see that? It's like 225 up here. So, right, so you got that. How about, ooh, now this is the same data, but a little bit funny looking. This is not x versus t. This is x versus t squared. And that does line up in a straight line. And see, the advantage of doing that is you can whip off slope real fast. You say rise over run, boom, I got the slope. It's like 24 centimeters per second squared in this case. And you can make an equation out of it, right? Accurate equation. X equals 24t squared, okay? Which also describes this graph because of the same data. That's right. How about mass versus time? What relationship is there between mass and time for the car? No. No relationship. I have lots of different mass cars, but they all take the same time to roll down that distance. That's it. Ooh, how about velocity versus time? You guys have a speed gate? Some of you guys had used a speed gate? Car zoom went through. Because if the car rolled for 3 times the amount of time, it picked up to how many times the speed? 3 times. Yeah, and that would be a linear relationship or a direct relationship. Okay. Some of you guys had this one. Ooh, guys, what shape is that called right there? A square root. Okay. So if you let the car roll for like 9 times the distance, it only takes up to 3 times the speed. Next, there you go. All right. Okay, and then here's the linearized version of that. So speed squared versus x linearizes. You can get the slope really easily, therefore make an equation. Figure that out. Okay. Okay, got some more. All right, so there's your graphs. So I could pull any of those. I know all of us did. I had all you guys make all 6 graphs. So I could ask any of those graphs tomorrow. Graphical relationships. Okay. If you do have a parabola, then well, actually, I think I got this for class later. Yeah, so this is not part of the review exactly. Okay, but you guys remember this quadratic formula maybe from a math class? Right? This might show up later in class today. Right? Right, so whenever you see a parabola motion, like height versus time. Speaking of height versus time, that sounds like a kinematic question, a linear motion question. So let's look at some of these. Right, so you guys have, oops, so this one is right. You guys have this page that says linear motion on it. Okay. Now I didn't realize this until this morning, but oops, I actually printed not the one I meant to print. Right. So this will still be the assignment. But do you guys see 10 different, or I guess 11 questions? Right, so much that 11 questions. Right. So the one I meant to print is actually an updated, better version of that, which is the one that's been posted on Google Classroom. So let me show you guys where that is. Now, again, the one I'm about to show you guys right now. Sorry, Google Classroom's being slow. All right, this works. Okay. The one that's posted on Google Classroom is not the official assignment because I didn't print it out, but it's the one I meant to. Okay. Okay. Yeah, this is not loading. But if I click on you guys, physics honors, and I go to the beginning of this week. Oh, here we go. Let's see if this shows up. Okay. To the beginning of this week, there's one says, you guys see linear motion puzzles and labs. Okay, I'm working on the projectiles, so I'm working on those you can't see yet, but these can. Okay, so it's one of, I think it's this one right here. Okay, is the one that I meant to pull up, and I did load that earlier, so I have it right here. Bam. Okay, so it's really similar, but it's better in some ways because every one of these scenarios I can actually ask two questions about. Like, guys, we're juggling these 5 variables: time, acceleration, displacement, initial velocity, final velocity. And you have to have 3 to be able to solve something. Okay, then somehow I have to give you 3 of those. Right? That means I could ask 2 questions about it. Like this one right here, I could ask how far, which is x, and I could also ask how fast, which is v final. Is that? Right. So here's what I do is, let's look at this page for a while. We'll pick a few questions off here. You know what, while I'm looking at this ball drop from a treehouse, I think that's a pretty good one to start with. Right. Also, I would not be cannibalizing the questions you guys have in front of you anyway. Okay. So yeah, let's do this pair of questions. Ball drop from a treehouse. All right, my computer's all frozen. Okay, so it looks like, guys, that word dropped right there. Dropped already tells you one kinematic value. What does the word dropped mean in physics? It means what is it mean what? Initial there you go. Initial velocity is equal to 0. Right. Now I did explicitly type that here. I said v initial is 0 meters per second. Right. But most textbooks would not do that. They would just say the ball is dropped. And you have to kind of figure that out. But you can figure that out. Right. Looks like I have this treehouse on Earth. I guess where tree houses are. On this page, I happen to use 9.8 meters per second squared for Earth gravity. No, more often than not in this class, I tend to round that to 10. But I guess this one, right? And it looks like it took 1 second to reach the ground. Okay. Now, once you have that information, there is definitely only one height of the treehouse above the ground, and there's definitely one crash speed. And that's the questions: is how high is the treehouse and what's the crash speed? All right, so move this here. Okay. All right, so let's draw this out. All right, got tree house. There's my tree house. I drop this ball, and it's going to crash land. Okay. So I don't know what the height is. That's one of the questions. Call this h. Right? What's the height above the ground? Or you could call it x, or you could call it y. Right. So be ready to use those interchangeably. Right. I know v naught is 0 meters per second because I'm just dropping it. I'd like to know this crash speed. What is v final? I know the time it took was 1 second exactly. Somebody timed it with a stopwatch. Right? So as soon as he lets go, they start timing. It takes 1 second to fall. Okay. And we're going to call Earth gravity 9.8 meters per second squared today. All right, so there you go. Now if I make a little checklist, like what do I know, what do I want to know? A little tax VV checklist up here. Okay. So I know A, acceleration is 9.8 meters per second squared for Earth gravity. I know V naught 0 meters per second because you dropped the ball. And I know time is 1 second because somebody timed it. Okay. How tall is the treehouse? And what's the crash speed? Boom, boom. You see that? All right, here we go. Right. Now to solve this, right, it's equation time. Now you guys know the whole Cardan incline lab you guys did. Remember, we took all that data, we crunched it, and eventually came up with these 3 governing equations here. Okay. So quick review. The first one tells you how far is a function of time. Okay. And if there's zero acceleration like cruise control, it's very simply just speed times time. That's all. Just going 60 miles an hour for 3 hours and went 180 miles. But okay. If you start from rest, it's very simply 1/2 AT squared. Right? And if you like give your car a push, so it has an initial velocity, or if I throw the ball straight down, then you just add those two bits together. Right? So how far is a function of time? The second one tells you how fast is a function of time, but doesn't mention how far something moved. And the third one says how fast is a function of distance moved, but doesn't mention how much time has passed. Right? So each of these could be advantageous depending on how the question is framed or what information you have. Right? Okay, so with all that in mind, what equation do you guys want to use to start solving this? First, second, or third? First, second, or third. What do you guys think? If you don't know, you can just pick one and run with it and see what happens. So let's say I pick the first one and just see what happens. Right? So let's go x equals v naught t plus 1/2 at squared. Just like that. Okay. Now this x really stands for this height. So place the x, I'm gonna put an h. Oh, I know this v naught 0, so that just goes away. Got 1/2 in the place of a.
Interruption, At this time, we are going into a shelter in place due to inclement weather. Please keep students with you. Shelter in place due to inclement weather.
Ooh, actually, that was pretty lucky, wasn't it? Because I don't even need any algebra. This is all arithmetic. I can just plug that in my calculator. Oh, and what does this come out to? Actually, you don't even need a calculator. What is that? Well, 1 squared is 1. Half of 9.8 would be 4.9. Okay. Now, guys, in this class, numbers also have units attached to them. What is meters per second squared times seconds being squared? Meters per second squared times seconds squared gives you what? Meters. Which describes the height change or displacement. Meters. Yeah, sure is. Right? Okay. Hang on. I think you guys have seen this before. I think you guys saw this recently. Isn't this the same as you drop a ball off a cliff? How far has it fallen in 1 second? Is that the same question? Okay. Now this one's rounded to g is 10 meters per second squared. Oh yeah, remember it was like 5 meters? You guys remember that? That's in your notes from yesterday, isn't it? Yeah, isn't it? And the other question is how fast does it crash land? So, right, so we've exhausted the first one. Right, and it doesn't say anything about crash speed anyway. Okay. What do you guys want to use for crash speed? The second or the third? Second one? Yeah. And really, at this point, you could use either one. You could do this one based on the fall time or this one based on the height change. Okay. And they'll both get you the same answer. Okay, let's go to the second one. So let's do v final, which we want to know, equals v initial plus a times t. Yeah. V naught's 0. Okay. So the crash speed is got 9.8 meters per second squared times 1 second. Oh, would that be 9.8 meters per second? Because meters per second squared times seconds brings me to meters per second, and that describes the speed. There you go. Which should be also consistent with dropping the ball off a cliff too, because isn't this again also this exact same scenario? Right? So then after 1 second, it's going, oh, there you go, 10 meters per second. Okay. Again, G's rounded a little bit. All right. All right, guys, good. Guys, good. All right, so we've got next. I want to pick another couple off here before we try something else. Okay. Let me scroll down to, let's do this scenario. So I'm going to stick to a tree house, except now we're going to throw the ball straight down. So ball's thrown straight down at this given initial velocity. Ooh, look at that. I'm throwing it down at 5 meters per second. I know the height of the treehouse. I got a 7-meter tall treehouse. And we're in Earth gravity. The two questions I want to know is how much time does it take to reach the ground? Say you got a friend down below. It's like, catch this. Bleh. Like, how much time does he have to react? And also, what's the crash speed? It's supposed to be different than before. So I'm going to write down that scenario. I'm going to copy those numbers while you guys are maybe also writing that in your notes. So I'm drawing a tree house in my notes. I'm doing this all off screen right now. Okay. Tree house, drawing a tree house. Okay, it looks like the height above the ground is 7 meters for this one. So I'll label that height H equals 7.0 meters. I'll call G 9.8 meters per second squared. And I know the throwing speed V naught is, say, 5 meters per second. So 5.0 meters per second. Okay. So that's what I know. How much time and what's the crash speed. So let's bring this back over here. Okay, so that's what I got. Okay. Those balls eventually going to reach the ground, of course. They're going much faster. So let's be final. And that's one thing to solve. The other thing to solve is how much time does it take? Okay, you guys get that? So a little checklist. Tax VV. So here's our 5 variables. Okay. I know the acceleration because that's free fall right here. Okay. I know the height of the treehouse, which is right here. Check, check. Okay. I know the throwing speed. Check. Okay. So how much time and what's the crash speed? Okay. Okay. So what do you guys think is probably the best way to navigate? First, second, or third? What do you guys think? First one? Your nomination for the oh. Ooh, this is gonna be fun. Ooh, let's do the first one. You chose interestingly. Yes. Let's go. X equals V naught T plus 1/2 of AT squared. There's no going back now. So, guys, let's have everything down be positive because the ball's moving down, gravity's pulling down, I'm throwing it down. So all the numbers will be positive. That's true. Right. So how far did the ball move from here to here? 7 meters, right? So right here, I'll put 7 meters equal. Right now, I know the throwing speed was 5 meters per second, and that's also downward. So that's why it's positive. Because if I threw the ball upward, then I wouldn't put 5 here. I would put what? -5. Because it would be reverse direction. Okay, so just think about that for that might be helpful somewhere. Now I don't know what T is, so got that. Plus 1/2. Oh, I do know Earth gravity. No, on this paper I'm calling it 9.8 meters per second squared. Okay, so use that. If I'm want to make sure I'm getting multiple choices right. So, all right, and, okay. I don't know this T that's being squared, so it goes there. Okay. So that's how that fits together, right? Okay. Okay. Uh-oh. Can I solve for T? I got a T squared here. I got a regular T here. I have another number over here in the mix. Can you solve for T? Yeah. Yes, you can. Yes, you can. How? What word am I thinking? Starts with a Q. Quadratic. Quadratic. That's this one right here. Quadratic. Okay. So I'm not gonna necessarily expect you guys to memorize this. If I want you to apply this, then I would give this to you. Right. But if I did, I would want you to know how to apply it, and that's what we're gonna do right here. Right. So quadratic says this. It says if you have a parabola, and this would be a parabola, right? Height versus time. Okay. In the form a t squared plus bt plus c equals 0, right? That's a condition, equals 0. Then this has already been pre-solved. T always comes out to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Right? That's always the solution. So how can that apply here? Well, I better rearrange this. So half of 9.8, I'll just call it 4.9. So that's 4.9 meters per second squared. T we're solving for squared plus 5 meters per second times t we're solving for minus 7 meters goes to 0. That would also be meters. Just like that. Yeah. Right. So all I did was took this kinematic looking expression with the numbers plugged in. I rearranged it so it looks like this form equal to 0. And therefore I can solve for t. True? True? Okay. You guys ready to push these numbers through the quadratic equation? Or make a quadratic equation? Because looks like b would be 5. You guys see b is 5? Yeah, so start -5. So open parenthesis, do -5. Here, this might be a good calculator exercise. Now I got a plus or minus here. So here, let's just pick plus and well, we'll start with that one. Square root b squared, so 5 squared minus 4 times, okay, my a is like 4.9 right here. And my c is, well, my c is -7. So gotta include the negative, subtracting a negative sort of thing. Close parenthesis, closes the square root, close one more parenthesis that closes out the numerator. So I really got parentheses galore going on here. And then divide by, and then 2 times a, so it's 2 times 4, 9, and parentheses also. 2a, right? True. Let's see what we get. So this says, yeah, that looks right. 0.78936. I'll call it 0.79 nosy seconds. 0.79 seconds. Okay. Let me say or, and if I scroll up, scroll over, and replace this plus with a minus, let's see what does that give me? It says negative 1.81 seconds. Okay. Which there is an interpretation for that too. It's like if I ran the film backwards in time, it's like where would it also be at ground level? And that would be the answer. Okay. But for our purposes, we just care about forwards in time. I threw the ball and it landed in the future, like it's 0.79 seconds in the future to reach the ground. Okay. And we make sure that's an answer choice. Is that an answer choice? Yeah. Bing! Right there. The answer would be C there, right? But we got one more question to go, which is what's the crash velocity? Crash speed, crash velocity. So, what do you guys want to use for crash velocity? First, second, or third? I think okay, third. I'm here, third. Yeah, actually, you could use either one of these because we just found the time. You can plug that time we just found into here and get that one, right? Let's do it both ways. Let's start with the third one. So vf squared, v final squared equals v initial squared plus 2ax, right? So I want to know this crash velocity. I know I threw it straight down at 5 meters per second. That's being squared plus 2, got 9.8 meters per second squared. And the height of the treehouse was 7 meters. Right there? You got pause for a moment before I start checking through a bunch of algebra. Okay. Is what if, it's ready for a symmetry question? What if instead of throwing it straight down, what if I threw it straight up? Man, yeah, like goes way up here and then comes back down. But I threw it at the same speed, just up instead of down. Okay. Here, see if I can figure this out before you look at the map. Okay. Now, obviously, the one I throw upwards is going to take more time to hit the ground than the one I throw down. And so I throw it down, hits the ground pretty fast. Throw it up, takes a while for it to hit the ground. Okay. But what about the crash speed? Because which crash speed do you think would be bigger? Or do you think it would be the same? So here, I'm going to see show hands. Is it the one I threw down, the one I threw up, or do they have the same crash speed? Like, which one's moving faster? Okay. How many guys think the one I throw straight down would be hitting the ground faster? Throw it. Okay. So throw it at 5 meters per second straight down, and it has some crash speed, which we're about to find out pretty soon. Or how many guys think if I throw it straight up at 5 meters per second and it goes way up here and then comes back? How many guys think that one hits the ground faster? How many guys think they'd be crashing at the same speed? Yeah. It is the same speed, right? In fact, in terms of the equations, because we almost got the answer right here. This 2ax, nothing of that changes because either way it starts at the tree house and it ends at the ground. Come on here, both goes. The only thing that would change mathematically is this 5 would change to a -5. But if you square it, it's the same either way, right? Because a negative squared is positive anyway, right? So yeah, same crash speed. In fact, all you need to do to finish this off is just take the square root. So it's the square root of all this. 5 squared plus 2, 9, 8, 7. This is some number of meters per second. If I pulled the unit out, wouldn't that be the answer right there? Okay. Let's see what it is. Square root of 5 squared plus 2, 9, 8, 7. I'm looking at 12.7 meters per second. That should be the crash speed right there. 12.7 meters per second. Let's see if is that an answer choice. 12.7. It is. It is an answer choice. It's 12.7 meters per second right there. Right? And one more thing I want to do with this question, let's circle back to this middle expression and see, does it give the same crash speed? Because it should. Let's see if it does. So let's go V final equals V initial plus AT. Now I know V initial, I threw it down at 5 meters per second. Down is positive, so that would be positive. Acceleration, gravity's pulling at 9.8 meters per second per passing second. And do you guys remember a while back, I was getting 0.79 seconds for the time? Okay, so I'll pop that in right here in a second. So what is this? What's 5 plus 98 times 0.79? Okay. I'm getting 12.7 meters per. Oh! 12.7 meters per second. That's what we got using that other kinematic formula. We got the same thing. That's it. Works out the same. Right? Okay. And what I want you guys to do too is remember here, I asked you guys to start off this question. What do you want to do? And you guys picked the first kinematic equation, which we could do, but we immediately ran to a quadratic formula situation. You guys remember that? Okay. You can also solve all this skirting around the quadratic if you instead start with the bottom two equations. Okay? Because if you start with the bottom two equations, then you can solve everything with just those. Okay, and then not have the quadratic at all. So yeah, different ways to go about it. There's different paths through the force. They all lead to the same answer. Right, now there's one more I want to do from this Google Classroom page. One more. And this last one's a little special. Because do you guys see the pattern for most of these is you identify what variables you have and what you want, and you just go equation shopping from that page with the 3 kinematic equations. Right. Okay. And you just plug stuff in and kind of navigate around until you solve everything. Right. But there is one that's kind of special. And it's this one right here, the very last scenario. Car brakes to a stop. Car brakes to a stop. Okay. It takes the given time and displacement for the car to come to a stop, find the acceleration that the driver experiences, and the speed of the car before braking. So if you look at this table, I explicitly typed out the numbers you know. Right? Because when you see brakes to a stop, that by itself tells you a kinematic value. What does that mean? That means what is equal to what? Yeah, final velocity is 0. Right. Again, most textbooks would not explicitly type out final velocity is 0. You'd have to figure that out, but you guys can figure that out. Right. So I did. I gave that to you. Right. It looks like this car took 30 meters of road to come to a stop, and also this whole process took 3 seconds. Now there is enough information embedded right there where you can determine how fast was the car going and how much was he slowing down. Well, it's the acceleration, which should be a negative value. Right? Okay, you guys get the premise? All right, so back over here then. Here's, let's say car brakes to a stop. That's the basic scenario. I'll draw a picture. So car, here's the initial velocity was, oh, actually, sorry, we don't know that. That's one thing we gotta find. Initial velocity. I know the final velocity is 0 meters per second. I know that from here to here, x equals 30 meters, because that was given. Okay? And I also know the amount of time that took was 3.0 seconds. That's it. That's it. Okay. But I do have 3 kinematic values. 1, 2, 3. So this is solvable in principle. Okay, you guys get that? Okay. Now, let's look at kinematic formulas. Suppose you went to your go-to method. Okay. Well, okay. I'm in trouble fitting this all on the same screen here, but okay. You start shopping around for equations. What do you think would be a good one to pick? First, second, or third? Okay. Let's say you pick the first one, right? So you pick the first one, you start plugging in numbers, running with it, see what happens. Okay. So let's see, I know T, X, and V final. Right. So okay, there's the T, there's the X. Right, V final's not in here, but that might be right. Oh, but I don't know the initial speed, and I also don't know the acceleration. That's 2 unknowns. If you have just one equation by itself with 2 unknowns, is that solvable? Not by itself. So, okay, so maybe I put that to the side. Okay, I say, hey, try the second one. So, I know the V final, that's 0. That goes right there. I know the time is 3 seconds. That's right there. But I don't know the V naught and the A again. Okay. You know what? The third one, I think it's going to be the same problem. There's the V naught and the A all over again. Okay. So this is the only scenario where you cannot start solving with a single equation because the v naught and the a are the only pair of variables that show up in all three expressions. You guys see that pattern right there? Right. So you can still solve this, but do you think you could maybe set up two equations instead of a system of equations? Right? Yep, you could totally do it that way. You could pick any two of these. Those two, those two, those two. You set up a system of equations, it'll get you there. Right. But there's I think a more elegant way to solve this one. Kind of an interesting, creative way. And that's to not use the equations at all, but to use a graph, velocity in meters per second as a function of time in seconds. Right? So we're going to solve this particular scenario with a graph. Right? And first I want to see if you guys can draw that graph. So you guys got that set of axes in your notes. I'm going to walk around the room and see who can correctly draw that graph for a car braking to a stop. Right? Actually, I should throw in a word uniformly. Brakes uniformly to a stop. And that means constant acceleration. So most physics textbooks might mention that word. Okay. Okay. Like it's slowing down at a constant rate. Okay. Car brakes uniformly to a stop. See, what would, and notice it's a velocity versus time graph, not distance versus time, not acceleration versus time. I'm just looking at velocity versus time. Okay. Maybe you can reason it out. What would that look like if you're braking to a stop? You're braking to a stop. I don't think we've done this graph yet, so you have to use some creativity here. See, because if you're braking to a stop, do you have some velocity at the beginning of the time interval? Yeah, because the car's in motion. But at the end of the time interval, how fast is the car going? 0. Ooh, that might be a hint as to one point on this graph. I know after some time, how about 3 seconds? 3.0 seconds, the car is sitting at 0 meters per second. I know that's a point right there. Right, that's a point on the graph. Huh. Oh, and at time 0, say the car was, when the driver just starts to apply the brakes, the car would have been in motion. So how can you represent that? Oh. Yeah, some initial velocity. There's a point right there. Right. Okay, so now I know 2 points on the graph. Right, the car was moving really fast at the beginning of the interval. Then time moves forward, the car slows to a stop. Right. Okay. What do you think is going to connect those 2 points? Straight line, straight line. Yep, straight line. Zip. That's the graph right there. Okay. Just kind of like, let me pull up your guys' car incline graphs. I need a v versus t, right? Okay, here's a v versus t. Velocity versus time for your car. No, your car was speeding up, so it's not exactly the same scenario. But guess what shape? Or maybe you remember what shape was v versus t for your car. It was a straight line. Yeah, it was linear. Yeah. If it was rolling 3 times the time, that corresponded to 3 times the speed it picked up. Yeah. Right. So normally in this class, v versus t graphs are straight lines. Right? And that goes hand in hand with this word uniformly that I popped in here. Okay, so yeah, there it is. Car was going fast, slows down to rest. Okay. Now, this v versus t graph. Here's another v versus t right here. Oh, this is a really information-rich graph because at any time it can tell you how fast you're going. That's just a coordinate. But you can also, like, different properties of this graph also tell you other physical properties. Right? Like, guys, what does the slope of this graph tell you? The acceleration. Wouldn't that be the rate change of your velocity? Would be called acceleration. Okay. Furthermore, what does the accumulated area under the curve tell you? How far it went. Yeah. Right. How far? Because here, how much time is the base? That's time in seconds. Okay. Because if you do speed times time, here, maybe this rectangle is pretty obvious. Because what's speed times time? Distance. Right? If you go 60 miles an hour for 3 hours, didn't you drive 180 miles? Right. That's just the area of that rectangle. Right? But it didn't have to be a rectangle. It could be any shape. Okay. In this case, we have a triangle. We got a triangle right here. So my 2 questions: what's the acceleration? And what's the distance the car, or no, sorry, I know the distance. What's the initial velocity? You can get from the geometry of a triangle. Okay. You guys see it? I'm hatching in a triangle right here. See if you guys have been following what I've just been telling you guys. What is the area of that triangle equal to?
Distance.
Yep. Distance stop, 30 meters. Okay, so this is 30 meters. The base of this triangle is 3 seconds. That 3 seconds is the base. 30 meters is the area. Hey, can you solve for the height of the triangle now as a velocity? Okay. What's the area of a triangle equal to?
8 times.
Yeah, 1/2 base height. Okay. So the area here I know is 30 meters. I got a half. The base is 3 seconds. And the height represents V naught. That's one thing I gotta know. What's 30 times 2?
30.
60?
Yeah.
Divided by 3 is
6.
20. Okay. And then it's meters divided by second. It's like meters per second. The initial velocity is 20 meters per second. Okay, see that? Okay. So now I know this is 20 meters per second. Okay. That's one of the answers, by the way. How about the slope is equal to the acceleration, isn't it? And isn't that, because how do you get slope? What divided by what? Rise over run. It looks like this went down 20 meters per second across 3 seconds. Like negative 6.67 meters per second squared. There's the acceleration right there. That's it. So 20 meters per second initial velocity, negative 6.67 meters per second squared, acceleration. Are those options? Here's the acceleration. Boom. Here's the initial speed. Boom. There. That's right there. Okay. This is good. Okay. Again, you could use the three kinematic relations also. Okay. Speaking of graphs, actually, that's an excellent segue to the last thing I want to do with you guys today, which is here it is. Okay. You guys' puzzles. So we did some that look like these on the front. Right? You guys can navigate the three kinematic equations right here to solve a bunch on the front. Okay. Wait, now on the back, I have some graph scenarios for you guys. Let's read these scenarios. The first one, a car starts at some origin point, travels in a positive direction at constant speed all the way to its destination. What is distance versus time, velocity versus time, acceleration versus time? The second scenario, the car starts from rest at some origin point, speeds up in the positive direction at a constant acceleration, then slows down at constant acceleration until it reaches its destination. Ooh, so it looks like it's always moving forward, but it starts out speeding up like, and then slams on the brake, but always moving forward. What does X versus T, V versus T, A versus T look like for that scenario? And the third scenario, a ball is dropped from the edge of a cliff, which I think we did those yesterday, didn't we? Yeah. So actually, this I think you have the answer for. Ooh, right. Here, I'll do one of these with you guys, and then see if you guys can figure out the other one. Because which of the first two scenarios do you want to do in class? First one or second one? Second one? All right, let's do the second one. Okay. Car starts from rest, speeds up, and then slows down until it reaches its destination, but it's always moving forward. Okay. Now, what I usually do is start with the velocity versus time and then branch out from there. You guys know all three of these are related to each other. So if you know one, you can probably figure out the other ones. Okay. So, okay, starts from rest. What does start from rest mean on this graph? Yeah, it starts at 0, 0. So 0 time, it has 0 velocity. Starts from rest. Okay. Then, if it's speeding up with constant acceleration, what does that look like? Yeah, straight line. So maybe something kind of like this. So it's accumulating velocity at a constant rate. That's what constant acceleration is. It's constant slope on a V versus T. Okay. And then slows down until it reaches its destination. Guys, slows down. Decrease velocity. You like that? Yeah, that's it. Now, again, in this class, velocity versus time usually it's like straight lines. Actually, we did just do this one, didn't we? Can we just, where is it here? There, down here. Lost my notes. Well, we just did that. We just did a car braking to a stop, didn't we? Okay, how about let's do acceleration versus time. You guys remember I told you here's this relationship. Oh,
Sorry, interruption, Hawk. We are no longer in a shelter in place due to inclement weather. Please do not dismiss students early. 3:30 is the bell, they can dismiss.
all right, we got 3.5 minutes. So isn't true the rate change of velocity that's called acceleration? And on a graph, the rate changes the slope. So the slope of V versus T tells you A versus T. Guys, what does this A versus T look like? You see a constant positive slope there?
Yeah.
What does that look like for the first half of this graph?
Oh. Diagonal going up.
Zip. And then braking at a constant rate. What does that look like on this graph? That constant negative? Have a jump thrown in there? Right. Now, if you're in a pure math class, they might want you to like a little open circle to represent a jump. Or if you were capturing this with the accelerometer, it might be very steep, like jump like that. Okay. But if you just left it like that, that's fine for this class. That's fine. Okay. So there's a few different ways to draw that technically, but if you just do that, that's fine. Okay. All right. Now the tricky one is x versus t, but I think you can get it if you put the two parts together. Like, doesn't this part of v versus t look the same as dropping a ball off a cliff? And what shape does that make on x versus t? Parabola. Yeah. So if you start at the origin point, it's going to sweep up like a parabola. And then this might be the trickiest part on this whole page. Is breaking to a stop. It looks like breaking to a stop. You start going really fast, so you cover a lot of road in some time. And then as you go slower, you cover less and less road. Now you're still moving forward, guys. You're not in reverse. You're still moving forward. You're just covering less and less road in equal intervals of time because you're going slower and slower until eventually you come to a stop. What does that look like to finish off this graph?
The downward slope, like you go up and then it starts going like that.
Okay, no, never,
It's called.
it never comes backwards. Because guys, if it came backwards, that would be putting part in reverse. Yeah, it turned well. It's an upside down parabola. Yeah, so it's a parabola with the vertex up here. Okay, so it is. All right. So I think you guys can probably figure out these other two scenarios, and I got some numerical questions over here. Yeah. Again, if you finish your quiz early tomorrow, which you might, then you guys got linear puzzles, and those are due on Tuesday.